Hello and welcome to the Applied Accelerated Artificial Intelligence course. I am Satyajit Das, so I'll be handling the introduction to AI systems hardware and system software, and I'll be taking some of the SDKs with PyTorch and TensorFlow. And yeah, so that's about it, and let's get started. So these are the contents of today's lecture. So basically, we will start with the introduction. We will see some applications of AI in modern days, just to get motivated in the beginning, and then we will talk about the computing systems from the perspective of AI. So from the perspective of running artificial intelligence benchmarks, what are the modern systems available and how they can scale, or how we can use them, and what are the shortfalls that are there, and how we can minimize the gap between the requirements and already available systems. So we will talk about those, and of course we will talk about some of the computing engines. We might not be covering all the computing engines that are available nowadays, but of course we will try to cover some of these and to see what are the things available nowadays. So let's see one application as Amazon Go. So basically this Amazon Go provides you the flexibility to have seamless shopping experience. So you go into one shop and you just take your things and you just get out of the shop, and your transaction will be automatically credited, and you will have this seamless shopping experience. A lot of AI is applied here. We will talk about what kind of algorithms or benchmarks that are being used. Another application is from this retail clothing scenario. So you go into one store and you, without any contact, you can just try out the clothing for your shapes and sizes that is available. So as you can see, you can just stand in front of the mirror and you can try out several clothes depending on your requirements and likings, and you can try it out, and you can have bought them as you go. So without even going into the trial rooms, you can have this seamless experience. Again, another application, of course, is everybody knows nowadays the application of automated cars. So basically, self-driving vehicles. So if you see different applications of computer vision and deep learning, you'll see it is most intense use of artificial intelligence in terms of application nowadays. Self-driving cars. Again, you have AI application in the area of medical imaging and automated operations. So based on the images that are available, you can actually have like which way will be the most efficient and reliable way to go into one tumor that is there inside your brain and inside someone's brain, and it can track that without any invasive measures, right? So these are the applications of AI, and there are numerous applications you have heard of. But the main question is, what is artificial intelligence? And here we have many definitions available, but mostly accepted definition was given by John McCarthy in the year of 2004 in one paper published from IBM, and it says that it is the science and engineering of making intelligent machines, especially intelligent computer programs. So the programs that are intelligent, that are not anymore the rule-based or conventional programming method, right? And it is related to the similar task of using computers to understand human intelligence. Okay, so that is the main purpose of emulating human intelligence into the machines through these computer programs or intelligent computer programs. But AI does not have to confine itself to methods that are biologically observable, of course. This is the generic acceptable definition of artificial intelligence. But broadly, it has evolved vastly from the earlier rule-based approach to solve intelligent problems to learning-based approach. And these learning-based approaches became very, very popular with the advancement of new computing systems that are like GPUs and FPGAs and different systems like that. So as I was mentioning that learning-based approaches to solve or to emulate human intelligence into computer programs have been very, very popular nowadays, and these are mostly widely named as deep learning and machine learning. Of course, we will use them interchangeably, and it is important to understand the nuances between them. Okay, so deep learning is basically comprising of neural networks which has more than 3 layers, okay, 3 or more layers. So it includes the input and output layer, as you can see here. And deep learning automates this learning process by extracting the features from the data available. And that is completely or mostly automated because this does not need the human intervention as much as the classical machine learning needs that intervention of human dependence, right? So that is kind of difference between these two concepts. But again, deep learning is one subset of machine learning, as you can see here, right? And now the most important thing is that what kind of computations or what kind of complexity these benchmarks have. And if we understand that, then it will be very easy to understand what kind of computing systems that we can engage them for, right? So the configurations or if you do not understand the complexity of the algorithm, it will be hard to relate to the computing systems that are underlying or that will be running your benchmarks, right? So all these from all these benchmarks that are available in deep learning, that are mostly neural network based benchmarks, but they are evolving day by day. And that is mostly because of different algorithmic innovation. So every year you can see hundreds, thousands of papers being published from the algorithmic innovation point of view in machine learning and deep learning and their applications. Of course, when I say applications, they are not confined to only deep learning or machine learning, that they can be applied to, let's say, natural language processing or text processing, signal processing, or maybe speech processing or whatever, right? But of course, these core benchmarks will be used for different applications, including the computer vision also, that application that we just saw as let's say in self-driving cars or Amazon Go or different other applications. So these algorithm innovations are happening along with the more and more availability of data. And nowadays we have abundance of data, and in terms of learning, the more data you have, intuitively your learning will be better. Okay, so the amount of compute or computation you need to do to train these algorithms are also getting more because you have more and more data, and you have to compute or you have to process those data into the systems that is available at your disposal. But of course the amount increases and the compute intensity also will increase, right? So now with these factors of advancement of AI, it is necessary to understand the computation complexity of AI algorithms, right? So this paper was published last year in archive preprint, as you can see here, and of course you will get to learn a lot about these neural network algorithms, with basics and different algorithmic innovations, as well as different systems that are available to process them. This is a good read. So in the reference, I will give a link to this paper. But if you see this graph shows a very uh, summarized way of representing these algorithms in terms of their computational complexity, right? So if you see the x-axis in this graph represents what? The top 5 error. Now, what is top 5 error? Top 5 error is that these algorithms are supposed to learn something, and depending on their learned parameters, or whatever they have learned for, so basically the parameters that we call them, or the model itself, they will produce different possibilities for your output. Let's say one classification problem. Okay, so these algorithms that you are seeing here, like efficient net, dense net, base net, and all these different DNN or specifically CNN networks or convolutional neural networks, they are supposed to provide you the classification of one data set called ImageNet. Okay? Now, what kind of possibilities they are producing, whether that represents the true class or not, so that is the measure of the error percentage. And top 5 error is if your top 5 guess of these algorithms lie in that your true class of this particular image or video that you are trying to classify, if they lie on their top 5 guesses, then how much percentage of time they can guess that. So that is the measure of this top 5. So that means if you want to increase the accuracy, so this is basically then the graph showing the accuracy versus the number of operations need to be processed for these benchmarks. And these number of operations you can see in the y-axis as represented as GOPS, or giga operations per second. You can see that in many places they are also referred to as gigaflops. So floating point operations also the same as GOPS, because all the computations will be in these benchmarks will be mostly for floating point arithmetic, right? So now you have top 5 error. You want to increase the accuracy of these benchmarks, and you need to also increase the number of computations that you need to do for these benchmarks to get more accurate. Now this blue line you can see here is the accuracy measure, right? It is linear. So if you want to get linear increase in the accuracy, the computations, you can see the evolvement of the computations get exponentially increased. Okay? And this is the factor you need to understand before going into implementation of these algorithms that you will see in the subsequent classes, right? So now this is one fact or one takeaway from this slide. You will remember that to increase or to get linear accuracy, you need to increase the computations exponentially, right? Now we will look into the computing systems that are available, and we will try to relate what kind of computing systems will be more suited for this kind of computational density or computational complexity that are being incurred by this AI benchmarks, right? So of course, traditional computing systems, as you know, that we have computation engine, and then we have memory. We have memory system, different levels or hierarchy of memory is there that we'll see in the next slide. And you have the communication unit. Now, if your memory is on chip, then you have on chip interconnect. And if your memory is staying outside, like dynamic memory, like DRAM or your storage system. So these are often housed outside of the chip, and then you need off-chip interconnect to get access to these memories, right? And if you see the hierarchy of the entire memory system in the modern computing system, you have the register file at the lowest end, and then you have different levels of caches, and L1, L2, L3, and then you have your main memory, which is your RAM, dynamic RAM, and then you have the swap disk to uh, uh, interchange programs between the swap disk and your main memory, depending on the locality or availability of the program, right? And that is mostly automated and uh, controlled by demand paging. So most of these concepts also we will see in the subsequent class in system software. But the most important thing in this slide to look at that the speed of memory accesses. Now, if you see in the register files, the memory access speed is highest. Then you have L1 cache in the range of nanoseconds. Then you have many nanoseconds in L2 cache, then some more nanoseconds in L3 cache, and few hundred nanosecond in your main memory access, so DRAM access. And then you have tens of microseconds to milliseconds in the access of swap memory or swap disk available. Now, in the modern systems, of course, your swap disk is extendable to your remote storage through different gateways that you can increase, and it can have several TBs, even petabytes of swap disks available. But just to look at the local system that you can have, the sizes vary from words to KBs to several MBs in the last level of cache, and then several GBs in your dynamic memory or dynamic RAM, right? Now, why this hierarchy is necessary? Because if you see the L1 level of cache, this gives you very faster access to the computing unit, because the computations are much more faster, and you need the data available to the computation unit much more faster than the dynamic RAM, because dynamic RAM, you can see the access is higher, right? The access time is higher. So the lower level you go, the access time will increase. The performance of access time will increase. That means you will get access in less time. And if you go in the upper level, the performance will degrade. And also, you can see that it can house larger size. Okay, so the sizes also you can see. Now, why this is important? This is important because the computation unit now see that that it has now that illusion of high or several level of memory is giving you like high volume. Okay, so larger space. So this illusion of larger space with very short access time is giving you this hierarchy. Okay, so this is why this hierarchy is important. Now, why it is important from AI computation or AI benchmarks point of view? Because from AI benchmarks, we have seen that we need a lot of data to be accessed for training these benchmarks, right? And when we talk about data, memory is the first thing it will come into mind, right? Because memory is where you will store the data. So what modern systems are doing is that, because if you see that access times will be very low for this L1 level of cache, then you keep it the closest to your computing unit, that your processor or core, and then you keep your L2 cache, then you keep L3 cache, and you can keep your main memory or DRAM and swap disk off chip. Okay, and that is what actually happening nowadays. And as I was mentioning, that the benchmarks are bottlenecked by the data access. Okay, AI algorithms are extremely data hungry, if you can see that how much data computation it needs per second, right? You have seen the graph before. So for these memory accesses, another key factor is the energy consumption. So size, the access time that we have seen in the previous slide. Now, from the point of view of energy consumption, this memory hierarchy is also important, because the more energy you will spend accessing memory, the more heat you will generate, and you need more cooling system to employ or deploy to cool your systems, and it is much more cost intensive than generating one system or chip, right? So that is why energy consumption is a key limiter of this data movement, and data movement is itself is energy hungry, because if you see this graph of uh, of the data access energy consumption versus data computation. So basically, these in x-axis you will see that these are the different operations. So of course, AI benchmarks or DNN benchmarks are widely dominated by addition, multiplication, and multiply accumulate. So addition and multiplication operations energy consumption you can see here, and DRAM access and SRAM access. So SRAM is static RAM, which technology is mostly employed in the caches. And for RAMs, your DRAMs, you can see DRAM access and SRAM access. The energy consumption is much higher, and if you go into DRAM, it is even several orders of magnitude higher than the computation itself. And if you just compare with add operation, this DRAM access needs almost 6400 times of energy to access this DRAM, right? So SRAMs or cache-based memory that are on chip, because they give you very short access time that we have seen in the previous slide. And now you can see here SRAM is also giving you much more energy efficiency in terms of memory accesses, and DRAM is giving you much more energy consumption, right? Now, this is the trend that you can see here, but what needs to be done? So modern memory systems, what they do is that, so they employ the L2 caches, the L1 caches inside the core itself. So in these cores that you are seeing here, core 0, core 1, core 2, core 3. So this is the core that is available, and inside these cores you have L1 cache. It is not particularly visible here, but L2 cache you can see prominently. L2 cache level cache you can see on chip, and then it has shared L3 level of cache on chip, and DRAM is a kind of off chip, because you need higher memory density, and it needs to deploy much larger space of memory. Okay. Now, if you see from the AI computation point of view, I will just give you one example of how much memory that are deployed inside the chip itself to get larger memory bandwidth for running the AI benchmarks. So this chip or this proposal was published in the year of 2019, and this is Cerebrus wafer scale engine. So basically, this whole chip is basically one wafer itself, and all the other chips that you see are basically separate. In one wafer, you will have several or separate number of chips. But this is a wafer scale engine, and this is one ML compute engine. Basically, it has lot of multiply and accumulate unit stored as or arranged as an array of processing engines, and these have this particular engine has 400,000 of this kind of cores. Okay, and on-chip memory, it has around 18 GB of on-chip memory. And this, if you compare the size of this chip compared to the GPU that are available, So the largest GPU that is available nowadays is NVIDIA's Ampere A100 GPU, and that has around 54.2 billion transistors. And this particular WAC or Cerebrus WAC is having 1.2 trillion of transistors. So you can imagine that how much bigger it is in size, and as well as uh, to accelerate, to accommodate all the computations that needed for different AI benchmarks that you have seen before. It employs 18 GB of on-chip memory, and that gives it 9 petabytes per second memory bandwidth. So 9 petabytes per second data that you can access. Of course, this is full precision data that we are talking about. Now, one next generation of this wafer scale engine was published in 2021, and that has 850,000 cores, and that can deploy 40 GB of on-chip memory and having 20 petabytes per second of memory bandwidth. So you can imagine how much memory it is employing. Okay, so just to have this shorter access time and reduced energy, and so all these things we have seen in the previous slide. Right? But of course, these are very highly specific ML accelerators or ML compute engine or AI engine. We will see much more generalized systems that are available and mainstream devices that are available. Okay. So that brings us to the section where we will talk about these specialized computation engines. Now, if you see from the computation engine, the processors. Okay, so is the basic computation engine, and as you know that you cannot increase the clock speed anymore due to the end of Turner scaling, and the power wall is hitting, and that's why you cannot get more than a particular fixed clock frequency that is available nowadays in the processors or computation engines. So how we will get much more compute density? So in terms of speed, we want to increase the density as well as computation engine, because you have to have the flexibility of including more number of transistors in a chip. So that is fine. And in terms of clock speed, also you cannot increase the clock speed anymore. So compute density you cannot increase after a certain limit. So what the traditional systems or the modern systems are going towards is that this heterogeneous computing. So where you have the serial tasks or mostly the parallel workloads, okay, which are not that much of data intensive. They are being controlled or they are being executed by the processor itself. So that might be multi-core processor, single core processor. So in this particular figure, you are seeing that it has dual core processor. Now, also in addition to processing engines to get the data parallel workloads executed, we have specialized computing engines. And these specialized computing engines are called accelerators. Of course, you will see several accelerators that are being used for particularly AI benchmarks nowadays. But in this slide, you can see that one GPU is there to handle these data parallel workloads, right? And one such accelerator or specialized system that you have seen in the last slide is Cerebrus wafer scale engine, right? So now the tradition is what? Divide your task into different subtasks, and of course the data parallel workloads. So mostly these AI benchmarks that we are talking about. So from the AI benchmarks perspective, these AI benchmarks or AI algorithms, those will be executed by these accelerators. So that is why we are talking about GPUs, and because of what that we will see in the subsequent slides. But the main important thing is that we have now accelerators in the system, in the computing system, with along with the processors. Okay, so that is the main takeaway from this slide. So now, what kind of accelerators that are available nowadays? So we talk about specialized computation engines for AI benchmarks, right? And over the years that you can see here, this graph shows the trends from 2012 to 2020, uh, and you can see now different computation engines. Okay, so we'll discuss them very briefly here. So what we have ASICs. So ASICs are ASIC engines or application specific integrated circuits. Okay? So these ASICs are mostly specialized, like highly specialized only for the AI benchmarks. And also we have GPUs available in this graph. Now GPUs can give you the flexibility to run both AI benchmarks as well as, let's say, video or graphics benchmarks as well. Okay. So now you can just try to realize like how much generalized way of computing that can happen. So you have the processors which are very generalized. So maybe the you can say the general purpose computing engine, like you can do everything in the computing in your processors. Now you have ASICs which are highly specialized only for AI benchmarks. Here we talk about AI based ASICs. Of course, for any other application domain, you can have different ASICs as well. And we have GPUs, which are graphics processing unit, graphical processing unit. So which has nowadays have the flexibility of accelerating your AI benchmarks as well. Why? That we will see in the coming slides. But you can see here what are the things available here. So ASICs, GPUs with FP32. So what is FP32? That is floating point 32. Now this is data type. Okay. So now data type and the accuracy that you have seen for the AI benchmarks have very close relations. Okay. So that relationship we will talk about, and you have your GPU int also 8. Int 8 means 8-bit integer units. Okay, GPUs with 8-bit integer units. GPUs with 32-bit floating point units. So 32-bit floating point units means single precision floating point units. You can have double precision floating point units as well, which will be then 64 bits, right? And these ASICs are a highly customized bit level implementation of computing systems for AI benchmarks. And that is why you can see that the performance density is much higher in these ASICs. Okay, because they are only specialized in running AI benchmarks only for given data type or given precision. Okay, so their performance density or GOPS per millimeter square, performance per area is much more higher. GPU is much more generalized in terms of it can both accelerate your AI benchmarks as well as your video processing as well, graphics processing, and it has almost closer uh, uh, or almost similar of performance density that is being achieved nowadays. And the trend you can see, right? So this yellow line is the trend for your GPU AP32, which is almost generalized GPUs that you can get in the market nowadays, and very few are. So basically, if you see that integer 8, so basically these are with having these GPUs with RTX 2080, T4, V100. So these are also having the flexibility to run your fixed point 8-bit, right, units. Now, what is the relationship I was talking about between the accuracy of the benchmarks, AI benchmarks, and the bit precision. Okay, so the more you have or more precision available in the computation for your AI benchmarks, the accuracy will be higher. So this is the simple relationship. Now, how you want to get higher computing density? You can reduce the size of the feature, right? So you can in this box here you can see that different sizes of feature map that is available. Now you want to have much more GOPS per millimeter square. Okay? So that is you want to accommodate much more compute, or you want to achieve much more compute density available for your systems. So you will go for uh, lower lowering your feature size, which is let's say 7 nanometer or 8 nanometer that is available. That CMOS technology that is being used to manufacture these chips like V100 series of NVIDIA GPU, and also around 28 nanometer is being used for this Dadian Nano. This is one ASIC based version of Dian Nano, which was published in the year of 2014, and in 2016 TPU was published. Okay, so first version of TPU. So this is Tensor Processing Unit published by Google, and that is also ASIC based. Okay, and you have Capricorn IRIS. This was published from the research group of MIT, EIE. So several ASIC-based implementations are there that you can see, and they use several feature map size. So basically, the size of these diamonds specify what kind of feature map they are using. Now, with decreasing the feature maps, that means you can accommodate more compute units inside your chip, right? So that means you can increase the performance density, GOPS per millimeter square, right? So how far you can go? Of course, you cannot go beyond certain limit. So feature map size or technology scaling you cannot do. Let's say beyond 1 nanometer nowadays, you cannot go beyond that. Right? So that means there is a certain level of performance density that you can achieve. So there is a limit that you can achieve. Okay? So that is the main idea that you will get from this slide. So the takeaway is, so what is the trend? You can see the trend of different computation engines in terms of GPUs. Here you can see what are their performance density in terms of GOPS per millimeter square, and also the systems that are available with different feature map sizes. Okay, so higher compute density will be achieved by lower feature map sizes. So that is the intuitive idea that is very easy to understand, right? So now you want to achieve. You have seen from the previous section that your compute density is kind of exponentially increasing. Okay? And your computation engine is kind of limited with these feature map sizes. You cannot put much more than that resource can allow you, right? So these are the two much more important conclusions that we will take away after this slide. Now, next, what we will do is that we will go into some details of evaluation of different GPUs from the mainstream NVIDIA GPUs that are available in the market nowadays, and their functional number of functional units that are available. So increased number of functional units. So you can see that you are increasing the performance density and number of bops or gigaflops per second that you are achieving much more. So currently we have Ampere series of NVIDIA GPU, which has several thousands of functional units that are available inside these GPUs. Okay, so we will see much more clear way, like in a very coarser array, like what are the things available and how you can program them, in the next lecture, but we will see some abstraction of these or some features of these modern GPUs which are available, and also modern ASICs which are available, and their performances, how they can vary. Okay? So in 2017, NVIDIA released V100, that is Volta series of NVIDIA GPU, and Ampere series of GPU was released in the year of 2020, and you can see that NVIDIA, in NVIDIA's terminology, this V100 comprises of 5,000, around 5,000 stream processors. So basically 80 cores with 64 SIMD functional units. Okay? And the Ampere series having this A100 having around 7,000 of stream processors, which can be interpreted as 1,108 cores with 64 SIMD functional. Okay? So these are the processing cores or this ASIM stream processors that you can see here. It is having L2 cache also, and it has also dynamic memory or DRAM, so which is this HBM2 that you are seeing here, and their interface that is available on this particular systems. Now, the basic difference of these two you can see here. Of course, in the microarchitecture level, there are differences that you will see, but from the memory point of view, you can see that L2 cache is now in the Ampere series. It is kind of banked into two banks. Okay, so L2 cache 1 and L2 cache 2, and here in the Volta series, the previous series having only one cache memory, and that is just to increase the throughput and reduce the latency of memory accesses. Okay, so now you can see that how much increase in the number of cores that can be accommodated into one particular system. Okay, so from 80 cores to 108 cores in 2 years. Okay? You can imagine like how much progress that is happening, and how these systems are getting scaled. Now, from the point of view of precision, you can see that the tensor this series of GPUs having tensor cores. Okay? So tensor cores for machine learning is available in your Volta series, NVIDIA V100, as well as your Ampere series, but this having new floating point data type as TF32. Okay, so that gives a bit more flexibility in terms of model training or benchmark training that we'll be discussing in the coming classes. But it supports also sparsity in machine learning computing or AI benchmarking. So these two are very important things to understand from the algorithmic point of view. Okay, so you can accommodate more number of computing cores, and now your cores also having tensor cores, which are specialized in machine learning. Now, if you see the NVIDIA core, one core itself, you can see that. So this is the core of V100. You can see that these are having this floating point 64. So this is double precision unit, integer units. So basically these are integer units for MAC operations. So all these are MAC units. So you can see here floating point 16, 2 will be multiplied and accumulated with the 32-bit of floating point, then it will generate 32-bit of data, right? So these are floating point 32-bit unit, as you can see here, and then along with these SIMD processing units, you have tensor cores. And what does this tensor core do is that tensor core actually does this matrix multiplication in one cycle. So basically 4 cross 4 matrix multiplication will be done in one cycle, one clock cycle to be precise. Now, why matrix multiplication is necessary, and why we are telling or why we are calling them tensor core. So basically the data is these tensor cores are employed or designed specifically to run AI benchmarks, which are deep neural network based or convolutional neural network based, to be precise. So these convolutional neural network based computations need the main engine is the convolution engine, and the convolution can be transferred or interpreted as matrix multiplication. It can be converted to matrix multiplication. So if you have matrix multiplication unit inside your SIMD of matrix multiplication unit, you can perform the entire tensor of like set of input data. So basically these two sets of data you can see 16 cross 16 plus you can accumulate another 16 which is already there. So in the accumulator, and you will get the data of 16 entire. So basically 16 MAC operations you are doing in the one set, and that is how you can increase the throughput in many fold. And that is the purpose of these tensor cores that are available in modern computing engines. Now we are talking about tensor cores. So that was the core available in the previous generation of NVIDIA GPUs, which are V100. And then we now have Ampere series of GPUs. And here you can see in the cores, you can see this register file is there, shared register file. And then you have this SIMD of integer 32, then floating point 32, floating point 64. So it supports all these different precisions of computations you can see. Okay. So all these units, basically this 32 unit, 32-bit fixed point, 32-bit floating point, 64-bit floating point, all these units are mostly used in accelerating your video processing and graphics benchmarks. And tensor cores are mostly used for your AI benchmarks. Okay. So that is why the modern GPUs that are coming with more number of tensor cores, and the tensor core in the Ampere series is even much more flexible than the earlier series. So there is a notion of sparsity inside your training or inference in your AI benchmarks. So what is sparsity? Sparsity means you can have multiple weights or parameters which are very close to zero, can be interpreted as zero. And if you think from computation point of view, so if you have, let's say, 4 cross 4 matrix multiplier, and if your, let's say, half of the data is, let's say, zero, then you do not need to compute those for those particular half number of multiplication. So that means, of course, that will be manifold for your 2D matrix multiplication, but you get the idea, right? So basically, for where one operand is zero, you just don't do the multiplications. So in terms of energy efficiency, in terms of throughput, you can increase it manifold. Okay? So that is why the sparsity in the matrix multiplication is introduced in these tensor cores that are available in Ampere series. Okay. Okay, so in overall idea, like voltage series, the T4 series, the RTX series, so what kind of performance or density they are getting with particular power envelope that you can see here in this table. Again, this table is taken from this reference, and of course I will give the link of this reference that you can go through after this class. But the main important thing is that you can increase the density. Here you can see only take particular for V100, and for V100 you can see that almost 10 times increase of performance density you can get just by using mixed precision. So mixed precision means in the whole computation engine you can have 8 to 32 bits of multiply and accumulate. And with full precision, full means the double precision, you can see the GOPS, and one order magnitude you can get more performance density in 32 bit, and even more you can get if you go for mixed precision. So precision, compute density, the energy, you can see all they are in the same power envelope. Okay, so in the same power envelope, without inducing more energy, you are actually getting much more performance density. Okay, but of course, again, just to connect to that graph that we saw before, is that you cannot increase beyond certain point, because the feature size you cannot decrease beyond certain. Okay, if you could decrease beyond certain point, then you will go to atomic level of feature map size, and but that is just theoretical. Okay, so beyond 1 nanometer, it is very difficult, because the energy, the temperature that will be generated by the processing engines will be much higher, and it will be hard to contain the amount of temperature that will be generated. Okay, so that's why you cannot go beyond a certain level of feature size scaling. Now, in terms of APGA-based accelerators, APGAs are fully reconfigurable, and this is the abbreviation of field programmable gate arrays, which are field programmable means these are mostly uh, bit level configurable devices. Now, in the APGAs, of course, you can employ different ASIC level accelerators because it is fully configurable. But this slide presents different performances of different ASICs that are available. So what are different ASICs that are available? We have the TPU, which is Tensor Processing Unit from Google. So V1 is essentially only was published for inferencing, but nowadays V2, V3, and other versions are employed in Google data centers for large-scale deep neural networks training. And all these computation engines that you can see here, they are essentially array of processing elements, or they are called systolic array-based engines. And these processing engines, as you can see, these are just array of multiply and accumulate engines. And to feed the huge number of processing engines, you can see 12 cross 14 multiplication engines that are being employed in one. This is the first version of the TPU we are talking about. And one scratchpad memory is deployed to just feed these data hungry processing engines. Okay, and then you have the off-chip DRAM uh, to offload the data to your scratchpad. So this is the kind of architecture of ASIC based accelerators or ASIC based specialized AI engines that are available nowadays. And this is one picture of Dadi and Nano that you are seeing here. And you can see that the GOPS that can be achieved is much more higher, with, of course, with you can see that how much power it is consuming. But of course, these are in terms of milliwatt, whereas the power consumed by these GPUs are in terms of watt, as you can see, because of course they are much more generalized in terms of computing systems, and these are much more specialized because these are only for they only deploy only these fixed precision or mixed precision multiply and accumulate engines only for these processing engines, and that is why they consume much less power, as you can see here. And of course, the FPGA based accelerators, as I was mentioning, that these arrays that you saw in the ASIC based accelerators, they can be actually configured or programmed into the FPGA to emulate one compute engine. Okay, so this is basically the figure of that array of multiply and accumulate processing engines and the memory hierarchy. And these engines are basically these convolution engines. These are operands, and then you have multiply and accumulate, and then you have the final the tree of the multiply and accumulate engines, and then you have the final output. Okay, so all these AI benchmarks are mostly to train your deep neural network benchmarks, to be precise. Well, from the market share point of view, so what kind of market shares in these companies have in terms of different engines like GPU and FPGA based? So GPU based, of course, market is vastly dominated by NVIDIA, 72.8%, and rest of the market is, so these are the stocks of after 2018 financial year. So now the ratio might have changed slightly, but overall you can get the idea. And then we have in the APJ domain, we have Xilinx, Altera, Microsemi, and Lattice Semiconductors, which has very few share. Well, these are the systems that are available nowadays. Now we are talking about the gap. So this gap I several times mentioned in the previous slides. We will just again go through this gap just to summarize whatever we have uh, studied so far. Right? So what is the gap about? The gap is about, so to get particular uh, accuracy level. So if you want to get linear increase in accuracy, okay, so you need to exponentially increase the computation density. Okay? So this is the takeaway. This was the takeaway from the uh, left hand side graph. And the systems that are available, we know that mixed precision and different precision we can employ, and we can have much more performance density. But of course, there is some limit, and we cannot go beyond certain limit of performance density, right? So so the trend to, if you see the computation requirement trend, that is going exponentially, and the resources that are available, the trend is kind of uh, uh, getting saturated, right? Because the feature size is almost going to your nanometer level, right? So now, how we can bridge this gap? We want to accelerate the AI. That means the benchmark that we talked about. So these benchmarks, like all these different benchmarks that we have seen, and few of these we will see in details in the coming classes, because we need to employ, or we need to implement them for a particular target device, right? Now the gap is there. Okay, so this computational requirement, or the requirement of the computational density is going high exponentially, and the performance density is getting saturated. So how we can accelerate some beyond certain point? Okay? So that is this course all about. We will learn how to accelerate the AI benchmarks that we have seen with the systems that are available nowadays with us, and how to employ several techniques from algorithmic to different configurations in training, how we can with different libraries, with different SDKs, how we can actually employ efficiently these benchmarks onto these systems. That is the goal of this course, and we will see the implementation, or how we can implement on these systems that are available in the coming lectures. So to conclude, we have these references. So you can see that we have the reference from Professor Mutlu. So you can learn about the memory systems, the state of the memory technologies that are available nowadays, and of course about the basics of these neural networks, the specialized computation engine, their performance, and how this scaling happening from the algorithmic innovation point of view, as well as from the system level point of view, and how we can actually merge them to get better computation and energy efficient computation, performance wise and high accuracy computation. For these benchmarks, you refer this paper. Well, that's all about for today. Thank you, and we will move towards first question answer session. Thank you.
Professor Satyajit, should I read out the question or you have access to, or you
I
would
can,
like? Yeah,
I
I have
can.
some of them are answered, and
Okay.
you can sort it on answerer. If you sort it on answerer, you will find your name there at the bottom.
Right,
So
right.
those are the ones which are left for you.
Yeah, I'm just.
Uh, can you see that the first question is what about VGG19?
Yeah, I'll just increase the window size. Just 1 second.
Yeah, and you click on the tab called answerer, so that once that organizer has already given, those questions will go at the top, and those
Yeah.
which are left for you are would be at the bottom.
Yes. So we have. What about VGG 19?
Yes.
Okay. Yes. So VGG has several versions available, 16, 19, 11, depending on the number of layers that are available. Of course, that is there. And VGG 19 almost rely in the same level as ResNet that we have seen. Okay, so the computation complexity is almost similar to that. Okay. What is top 5% error? So I discussed that. Again, I will just repeat it. Who did not get that? Top 5% error is that, so your AI benchmark or your DNN needs to guess. Let's say we are addressing one classification problem, whether your given image or let's say given image, we are talking about images for now. So given image is, let's say, dog or cat, or let's say there are 10 classes, right? So you want to you want your algorithm to guess what, or give some probability uh, values to these guesses. So higher probability will have this top one, then the next probability will have the second guess, third guess, fourth guess, fifth guess, and so on. Now this image is one lies in one true class. It cannot lie in all the classes, right? So you are addressing classification problem. So now this true class, whether it is lying on the top 5 guess of that algorithm or in what types of applications is it used for?
The same
So
same processor is referring to, yeah, Cerebrus.
sorry.
He is referring to the same processor what you just now described.
Cerebrus processor. Okay, Cerebrus processor. Yeah, Cerebrus processor is used for accelerating your deep neural networks. Okay, so high level of the, so it can You can train entire data set of video that are available for you, and so 40 GB of on chip memory that is available. You can imagine like how much data you can actually push for the data deep neural network training. So this is utilized for deep neural network training. So different deep neural networks that you have seen in the slides, and many more are there. We have, I mean, we did not have the flexibility to, I mean, it will clutter the space, and uh, it will be hard to read because of that we did not include all the available benchmarks that are there. But of course, this Cerebras supports wide range of deep neural network accelerators, even several autoencoders, decoders. I mean, there are plethora of deep neural networks that can be trained using this processor. And in large scale training, like with video, images, speeches, audio signals, so different data you can use for this neural network trainings. Now, next question is: does GPU programming aid us anyhow, or for to achieve high computational density? From the programmer's point of view, yes, you will get the flexibility that we will see in this course. So that is the purpose of this course, is to from the implementation point of view, how we can utilize the mixed precision available, the compute engine that are available inside the GPUs, and how we can use them, how we can train them, how we can increase the computation density, how we can increase the throughput, decrease the training time. Of course, accuracy will be different depending on different data types that you are using for training. But yeah, I mean, we will see how to use that and how to implement that from programmer's point of view. Uh, Next question we are having: can you give examples of AI ASICs? What are the inner components? Yes. So as we have seen in the TPUs, right? So TPUs, Dadian, Dano, even Cerebras. Okay, so these are the ASICs, example of ASICs that are specialized for AI benchmarks. TPUs are widely deployed in Google data centers, so they use TPUs. And the architecture of TPU that I discussed, that array of processing elements you will have, and those processing engines are essentially multiply and accumulate engines to leverage on the uh, uh, architectural aspects of convolution neural network itself, to explore them, exploit that parallelism in several layers, and then you can have. Now there is one ASIC also from NVIDIA as well, NVDLA, Deep Learning Accelerator. You can see the details also. And also several accelerators are available, and day by day more accelerators are coming. Iris is one of the accelerators very widely used in academia for research, and as well as companies are adopting in increased manner. So this Iris, several versions, V2, V1, V2, V3 is there, and that is from the MIT's AI group. So these are the ASICs, AI based ASICs. Okay, SIMT execution was mentioned in the slide NVIDIA V100. And yes, SIMT is the term that NVIDIA uses, but this is nothing but CMD operations that you have read. Now, this is essentially the abbreviation of single instruction, multiple threads. So basically, these threads are nothing but combination of uh, different sets of data, or array of data. Okay, so now each like several SIMD processing will have combined as warps, and then you have the threads for these stream processors that we have seen. But that is very much specific to the terminology from NVIDIA. But you can think it of very fine-grained, you can think it of as SIMD units. Okay, as simple as. What does fixed quantization refer to? Table in overview accelerated slide. Yes, fixed quantization is essentially uh, transforming from one precision to another precision. Okay. Now, whether you are operating in fixed dynamic range or floating dynamic range, depending on that quantization, you will have different data types in it. Okay, so this is again one implementation approach to increase the computational density in with some accuracy loss, of course. Feature size is limited by temperature, cooling abilities. Okay,
I will
so this
answer
is
that
from
question. No, I will answer
yeah,
that question. If he is
yes,
referring
yes,
to the feature size inside a chip, then day by day, smaller and smaller feature sizes are being done. So this is a function of a of something called as lithography. So lithography, it's, I mean, you can crudely look at it like a photography. These days, it's all digital photographs, but earlier you had this kind of films, and from the negative you would produce the positive. So look at it in a similar way, but imagine that there are lines on that particular film. So through this, if the line is thinner and thinner, then the feature size becomes smaller and smaller. So it has nothing to do with temperature as such, because temperature will be determined by how much current, what is the frequency of operation, how much current is flowing. So whenever there is a current that is flowing, as per the I square R function formula, you will get the that will be converted into the in the temperature heat. So it is not limited by temperature, but there are, it is like what ability the machines have to draw thinner and thinner lines. So once upon a time, like maybe couple of years ago, 9 nanometer was the best one could draw. Then that becomes 7, 5. Now we are
approach with the TPU and the GPU based approach that you are asking for. These two will have several levels of or several sizes of on-chip memory. Okay. Now, while you are designing your training of your deep neural network, you need to know how much memory you are going to induce for your GPU, or if you are working with TPU, how much it is. Okay, so depending on the size that is available, you can flexibly program your neural network training to offload that much of data at one time or at one batch. Now, let's say you have it is I am not confining the discussion to only million records. Okay, so let's say you have more than that of the size that is available inside your TPU or GPU. So then what should be done? So that is the main question that we should be asking, right? So whether which will be better or which will be the better approach to solve this issue. Now, solving this issue is again from the programming side, how you are allocating the memory for your data. Okay? So if you are allocating more than that is available, then you will be actually going to and fro from your dynamic memory and then your on-chip memory that is available for both in TPU and GPU. Okay, so the approach is similar. So you need to know how much is available, and depending on that, you need to you need to resize the batch that is you are going to use for the training for your deep neural networks. And while training these neural networks, that we will see in the implementation, when we will do the implementation of these networks, we will see that how much data we have, and how much data we can actually allocate for each batch of processing in the GPU. If you don't do that, then your training will take a lot more time than it is expected. And that happens to students when who are not exactly who do not know, or who are not particularly aware of the system that is underlying, and they just blindly run the model without knowing the batch size that they need to allocate and things like that. Their training gets longer, and it takes long time to run it. And that is very important, like important factor, or important parameter that you need to take into account while designing, or the I mean while implementing the network itself in program. And of course, now you can now see that how much of memory that you have, then how much data you can address for these batches. Okay? So that can be millions of records, billions of records. How much precision you are allocating for the data, whether it is image data, whether it is other kind of data. So how the data will be accessed. So all these things will come into picture while allocating the sizes of these batches of this string. Now, that was in context of linearity, VGG19. Okay, so yeah, VGG19 we discussed about that. Will the study material and recorded lessons be provided? I hope that this
Has been
was
that is
answered before.
yeah, that has been answered. So don't worry about non-technical questions.
Okay, so next question is, deep neural network generally applied on big data sets. Is there any possibility to apply on smaller data sets? Well, if you are asking this question from research point of view, yes, we can apply, and newer techniques like zero-shot learning, few-shot learning that has come, and we can use deep neural networks with smaller data sets. But ideally, from the classical definition point of view, if you see that to learn the features, so basically in deep neural networks, you are learning the features automatically, and you do not need any tuning of hyperparameters, just few parameters in optimizer and things like that. They're there, but vastly you will not be intervening while training the neural network for the features that they will learn. Now, if you see from the machine learning point of view, there are a lot of human intervention it needs to be required, because the domain knowledge, or the features that we want to learn, some definition, or at least some features that you need to predefine before going into that problem. So from classical machine learning point of view, yes, with smaller data sets, you can do that. But learning features automatically will need, if you want higher accuracy, intuitively, you need much more data. So that's about it. And that's why deep neural networks need a large amount of data. Okay, uh, yeah. So next, will the study material of, okay, again,
But don't
this
worry,
same question.
don't worry
Yeah.
about that. We have already answered that. Okay, don't worry. There is it's mentioned in the FAQ how it is being done, and we have answered it multiple times. Still, they are asking. Okay, they don't
Right.
refer to the previous answers.
Okay, thank you. I
We'll
don't see
just
any
wait for
further
2 minutes.
question.
Yeah, we'll just wait for 2 minutes in case there are any questions.
Yeah, sure.
So I think the session was good, and there were quite a few questions with regards to what you said, and that's really nice.
layers that it needs to get generalized for, because the so when we will implement the algorithms in practice, you will see that the data the data that we will use, we will segregate that for training data, validation data, and test data. Now, to get generalized for the test data, which the neural network have not seen before, to get generalized idea about unseen data, the more number of data that will be needed to train the neural network itself. Okay, so that is the basic principle of the algorithmic working of the deep neural network itself. So that is not only that you need less data just to get. I mean, if you just have features available or idea about features, that is not the case, because this is from the algorithmic implementation point. So this is the algorithm, how the algorithm works. Okay, and the classical machine learnings like SVMs, the support vector machines, other like your ensemble based learning techniques. So all these techniques, you will see that there are a lot much more hyperparameters that you need to tune just to get these features learned by these models. So it is purely the algorithmic working or the way the algorithm works. Okay. So from the deep neural networks point of view, since you have deep neural network, so that means multiple number of neural network layers, and the number of parameters are also high, which will be learned. Okay, so millions of parameters it will learn itself. So that is why the number of data is high. And okay, so we have a few more questions. I just lost track of, I think. So I got it. So if we don't, okay, so this we just answered. Is there a way to expand to number of cores when neural networks is running? Okay, so you are asking whether you can expand means you can increase the number of cores that that are available when. Okay, so number of cores inside of one particular computing system is particularly fixed, because you have, let's say you are working with GPU, so you have 80 cores, and they have, let's say, several threads, so that is fixed, so you cannot increase that. Of course, now if you want to utilize all of them, of course there are algorithmic approach to increase the utilization of the cores that is available. Okay? So that you can do, but you cannot increase the. Now you can increase the number of core. GPUs, basics of APGS, so all the references you can get in that article. So the link is also provided. So once you have this, the PDF of slides, you can click those references and you can download the PDFs that are openly available, and you can access that. You can read that. How could we choose the value of hyperparameters? Yes. Of course, the hyperparameters in in the deep neural networks that we will see how to choose that. There are some default values that we can go with, but of course there are advantages and disadvantages, like how faster you can converge to your particular accuracy. So all these things are there. Details will be discussed when we'll talk about implementation, how to tune or how uh, uh, we can change. Also dynamically you can change while the training is going on, as well as statically in the beginning itself you can set it, and you can have many runs to statically change the hyperparameters to get the desired results in desired time. Is there any thumb rule for how much is the size of training and test data? Yes, there is thumb rule, but I personally I do not. So there is 70, 20, and 10. Okay, this is the yes, there are many cases where we have a very limited set of data where deep learning cannot be applied. Like let's say certain bursts, solar bursts that happen in millions of years. You do not have enough data available in our disposal, even in scientific community or in industrial community. So now what people usually do in those cases, they generate their own data. Okay, and there are many algorithms for generating data, like generative neural networks are there to generate a new set of data. There are other image processing techniques also there to generate image data if you are particularly working with image data. Other signal processing data also you can generate with GAN. So this kind of networks you can use for generating data, and you can use your deep neural. How to fine-tune the layer of parameters of an existing CNN for a particular task. Again, tuning the parameters that we will see in the implementation. Okay, all these things we will cover. Not much different initial aim. Basically, how to customize existing neural network. This is the next part is very important, because the question is how to customize the existing network to our need. So this is one very interesting thing. So you can so again, always it is about the accuracy you want, the outcome you want, okay, how much accuracy you want, and how much resource you have at your disposal. So depending on that, you can also decrease or increase the number of layers for a particular available model also. There are transfer learning even for efficiently train the neural network without using all the layers that are available. Okay, so there are several techniques available. You will see transfer learning in this course. You will see how to actually reduce or increase the number of layers, or how to customize basically the network. Okay? So yeah, this is very good question. What other good cloud platforms available to run or play around deep neural network execution apart from GCP? Yeah, Kaggle is there. Google Cloud Platform is there, so you can use. Mostly people use GCP. So yeah.
I think that is the end of questions. So thank you so much, and there have been a lot of messages of appreciation
Yeah.
for the lecture. And thank you all.
Thank
please
you all.
spread the word around that you should attend all the lectures live. Okay, thank you very much. I will now end the webinar. Okay, bye
Thank you,
everybody.
sir.
See you day
Thank you,
after
bye.
tomorrow.